Okay, everybody. Today we're going to start in on derivatives. We're going to do first the derivative by definition, and we're going to talk about the concept of what's going on, and then we'll get into some of the formality of how all of this stuff works. What I would like to say is don't freak out just because we're starting into the calculus content. Instead, just realize that the calculus is just an intense version of the algebra that we've already been doing. So you already know most of the stuff that you need to know coming into here. We've covered it in reviews and stuff like that. You just need to be able to apply it. So here's the concept that we're going to be talking about. Um, Say that you have a graph and on a normal old XY coordinate pair. And we're just going to start with the basic quadratic that we are used to, y equals x squared. We know this guy makes a parabola, and we know some points that are in there, right? So, well, if I had a better drawing, 1, 1 should be in there, 2, 4 should be in there. These are points that we know, okay? If I put in x equals 1, I square it, I get out a 1. If I put in x equals 2, I square it, I get out a 4. You could come over here and make yourself a t-chart if you wanted to. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and on and on. And those are the positives. We also know that 0, 0 is on that graph. And we also know there are some negatives like -1 and +1, right? That's a point on our graph. -2, +4, and so on. So the idea that we're going to be dealing with here is we want to find, and again, I'm going to come back to that difference quotient stuff we already talked about, the average rate of change. Okay. Find the average rate of change. And again, we're going to call that AROC, AROC. Okay. We want to find the average rate of change on a graph that isn't necessarily a straight line. Okay. So, in other words, the stuff that we've been dealing with so far, we found things. Hey, remember we have a slope formula. So recall m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And you use this all the time whenever you're talking about a straight line, right? Okay. This works for linear equations. So the idea here is average rate of change happens whenever we're doing this. Let me give you a couple of other things you might see. Um, as we get on into some calculus type stuff, they might use this little triangle and they might call it delta. You might see that in there. And it just means the change in y over the change in x. Okay. But it all is the same thing. It's all the slope formula. So here's the concept. If I had a straight line that went between this point 1, 1 and this point 2, 4, let me try to be as good of an artist as I can be here. I apologize. Okay. We would have a straight line in there. The concept is this. If we, and it didn't go through that point, I'm sorry. If we look for the average rate of change on the parabola, it's fairly close to the rate of change on the slope of the graph of the line, right? Okay. So the concept is that the average rate of change on a curve can be, not always, but can be approximated by using a straight line. Okay. So when we're talking about average rate of change, there's actually this thing, it's called a secant line. So let me scoot on up. A secant line occurs when a straight line crosses through a curve twice. Okay. It happens exactly twice. So that's kind of a definition. I'm going to move this. So if you need a pause to get that, go ahead. So up here, when we're looking at this parabola, assuming that my straight line went through both of these points, that's a secant line, right? Okay. So the idea that we're going to work off of is, first of all, is it fair to say that the slope of this line is somewhat close to the rate of change going on in this parabola? I think it's pretty close. But if it's not, then maybe we can pick another point, okay, another secant line. So there's got to be one here that's 1.5, a point, whatever 1.5 squared is. And if I drew between a line between those 2 points, the 1.5, x equals 1.5, and the x equals 2, I think that even approximates it even better, right? And probably I could find another point in here, maybe it's 1 3/4, and draw a line there that approximates it even better, okay? So the closer together the 2 points are, the better the approximation from the secant line to the average rate of change on the curve. Okay. So there's this idea that's out there that says, this is the concept, that says, okay, if you have a secant line, we have an approximation. If we move one of those points closer, we have a better approximation. If we move this other point closer, so we're getting closer and closer and closer to where x equals 2, the closer I get, the better the approximation is for the slope of the secant line to approximate the actual average rate of change that's going on the curve. Okay, so let's look at this. Let's do a couple of these and see. Okay, so we've got this parabola. We know it's y equals x squared. We've got 2 points. So let's find, first of all, the slope between, um, find the m when we have 1, 1 and we have 2, 4. Okay, so that's kind of the idea of what I'm asking you to do here. Okay, so m equals, well, we go y1, let's call it, or y2, let's call it 4, minus y1, let's call it 1, over on the bottom, x2, let's call it 2, minus x1, let's call it 1. And notice that I'm deliberately starting with the second point here because those numbers are bigger. So I know when I do this subtraction, 4 minus 1, I'm going to get a positive number. And when I do this subtraction, 2 minus 1, I'm going to get a positive number. I did that on purpose. If you did it the other way, you had 1 minus 4, 1 minus 2. It's okay. You'll just have -3 over -1. And we know a negative divided by a positive, a negative divided by a negative is a positive. So you'll get the same thing. Okay. So what we're seeing here is that the slope between this point and this point on the secant line, m equals 3, right? Okay, so that's a pretty steep slope. But what we said was we think it's going to be a better approximation whenever we put in 1.5. So let's see what that looks like. Okay, so we're still going to use the 0.24, But now we're going to use 1.5, and I don't know what that is squared. We're going to punch it on our calculator and see. Oops. 1.5 squared. 2.25. I should have known that. 15 squared is 225, but that's okay. 2.25. There's my 2 points. And we're going to do the same process and find out what that slope is. Again, 4 minus 2.25. On the bottom, it's 2 minus 1.5. Okay. 4 minus 2.25 is 1.75, right? Yep. Okay. And on the bottom, I've got 2 minus 1.5, so that's 0.5. And there's a little thing in your number sense, hopefully you know. If you're dividing by a decimal or a fraction that's smaller than 1, it actually makes this bigger. Okay, so be careful about this. It's not going to be smaller when I divide by 0.5. It's going to be bigger. So sure enough, there it is, 3.5. Okay. And so whenever I move those 2 points closer, I kept the 2, 4 the same. When I moved this point closer and made it 1.5 comma 2.25, I see it's even steeper. So the average rate of change on that curve is even more so than what it was whenever I used those first 2 points. Okay. So that's the idea we're going to be dealing with here. And it's all about using something we already looked at, which was called the difference quotient. Okay, if you don't remember, there were several steps that went into this, and it looked like find f of x plus h minus f of x divided by h. And if you don't remember, that's how we said we were going to find the average rate of change, or AROC, whenever we're looking at a graph that's not linear. Okay. Now, what you should notice is the difference. What's going on here is we're going to have a difference between 2 points, and we're going to find the functional value whenever we look at okay, we have the original x, but now what about the gap between the two x's? So here's the idea there. Say that my original x is 1. Okay. So if the original x is 1 and I want to do exactly what we just did a minute ago, so I'm going to use f of x equals x squared. Okay. That's the y. Remember, y equals x squared. I can tell you it's a function, f of x, so that's the notation. Okay, so what if x equals 1 and I'm using this as my functional value? Okay, and I want to look at this difference quotient. So what we know is we can come over here and we can say, okay, well, the average rate of change is... Okay, the functional value of x plus h. Okay, well, what does that tell me? Whenever I see this as my f of x, instead of writing x, I'm going to plug in x plus h. So it's x plus h squared, and we'll come back and deal with that in a little bit. Okay, minus, because there's a minus in the formula, f of x, which is the original function, which is just x squared. Okay, all over the H. Now, we did a little bit of this when we were doing the algebra review. Okay, so, okay, what happens here? If you don't remember, a lot of people think that that's the hardest step. So let me do this one separately so we can see what's happening. This is really saying x plus h times x plus h. When I square something, it means that thing times itself, right? And don't forget that to multiply this, I need to distribute x squared plus xh. Distribute that guy through, plus hx plus h squared. Okay, and these two are actually the same because they have the same variables. So this x plus h squared guy is x squared plus there are 2 of these. I'm going to combine like terms. 2xh's plus an h squared. Okay. So, you're going to have plenty of opportunity on this homework set to work through this, to make sure you got it, to see what's going on. If you need to, go back and remultiply this over and over, but you're going to see a pattern. If it's x plus h squared, it's x squared plus 2xh plus h squared over and over and over again. And then if there was some number being multiplied, like a 3 multiplied out in front or something, then you'd need to distribute that as well. But this is just this piece right here. So what we have here, if you remember, average rate of change is we have x squared plus 2xh plus h squared minus x squared, because that's in the formula, all over h. Okay. And what happens, and we see this over and over and over again, so we start getting used to this pattern. What happens is that anything that doesn't have an h in it, we'll see this exact same thing here. I've got a positive x squared, I've got a negative x squared. So things that don't have h's in them, those are going to go away. X squared minus x squared is just 0, right? And then I'm going to be left with things that have h's. So 2xh plus h squared all over an h. And what I see is there are h in both of these terms. So I'm going to factor that h out. There's that F word that some of you don't like. Okay. Double check me. Is this the same? If I multiply the h through, h times 2x, sure, that's 2x h. H times h, sure, that's 2h squared. So we're good. And what we see here is there's an h on the top, there's an h on the bottom. Those will reduce out. Okay. And then we're going to be left with something 2x plus h that we can work with. Okay. So I did this average rate of change thing. I've got 2x plus h. Let's go back and look at the original function that we said. I said, what if x equals 1? Okay. Because that's the point we started with. Well, let's plug that in. So we're now wanting the average rate of change at x equals 1. 2 times 1 plus h. That's 2 plus h. Okay. Now, the other point that we used earlier, so I have x equals 1. The other point was 2, right? Okay. X equals 2. Okay. And we had to figure out what the y value was. Okay. So what's the difference between 2 and 1? The gap there is my h. It's a 1. Okay. So right now I'm just confirming what we already know, which is that when I put in h equals 1, I get 2 plus 1. That's a 3. Hey, that's what we got whenever we went between the points. 1, 1. M equals 3 between 1, 1 and 2, 4. Okay. So we see, oh, that's actually what's happening here. Okay. So we get the same answer. Okay. But that H is going to change. And that's kind of the idea of what we're going to be dealing with here. The H we saw, hang on, let me get that picture back. The gap is growing smaller and smaller and smaller, right? Okay, so what happens, and we could go, since I'm using x equals 1, we could go between 1 and 1.5 also, right? So what happens as that gap gets smaller, we're going to get a different, oh, excuse me, we're going to get a different slope, and we're going to get a closer approximation to that curve, okay? So that's the background idea of what's going on here. Let's make a little note. H is the difference between your original x value and the second x value. So it's the gap between your 2 points. That's how I think of it. The x values. Okay, that's what the h is. So we're gonna play with that a little bit because um, right now we're totally dealing with okay, what's going on when I look at an average rate of change, but in a little bit we're going to talk about an instant rate of change. So here's another point for you to work on. We're going to stick with the same stuff. Y equals x squared. Okay. And we're going to now talk about between the points, find the average rate of change between 1, 1, which we already did, and 3, 9. Okay. So again, you're going to look at this and go, okay, my x equals 1. But now what's the gap between 1 and 3? The h equals 3 minus 1 is 2, right? Okay, so you're going back to what we did. You don't have to start over. We're using the same functional value, right? The f of x. So you don't have to start over from scratch. You can just come back here to where we found the average rate of change is 2x plus 1. I'm sorry, 2x plus h. I pointed the h, but I said the 1. 2x plus h. So very quickly, you can find up what's the slope between those 2 points. A rock equals 2 times we said let x equal 1, plus we said let the h equal 2. Okay, this is 2 times 1 is 2 plus 2. The average rate of change between 1, 1 and 3, 9 is 4. Oh, it changed again. There you go. And that's what happens. It depends on what x value I start with, right? And how far up I make the gap between them. All right. So why do I care about this average rate of change and things like that? Okay. So assume you're driving a car. Okay. And you want to drive you when you leave your house, you're at the 100-mile marker. And you drive for from 1 p.m. to 3 p.m. Okay. And at 3 p.m., you see mile marker number 210. Okay. And here's my question. You've been driving for 2 hours. Have you been driving the entire time at, say, 50 miles an hour or 60 miles an hour? No, because what happened? You get out on the road, you're going between here and say Texarkana, and you're driving, I don't know, 80 miles an hour, and then somebody cuts off in front of you in the lane in front of you, and all of a sudden you have to slow down to 55, right? Then they move over, and then you get behind a car that's going 75, and you go 75 for a while. Then you have to move over to let somebody that's speeding get past you. So you slow back down to, I don't know, 65 or something like that. So while you're going, I mean, if we were looking at your speed, it might go like this, right? Okay, who knows what's going on? Okay, but we know where you started at 1 p.m. and we know where you ended up at 3 p.m. And what we'd like to know is your average rate of speed. Okay, so your average speed. That's what we're thinking about. Okay. So the idea becomes, well, I know this isn't really a straight line. I know my speed was doing up and down, but can I do that and say, hey, let's let this secant line represent the average rate of change or the average speed? Well, sure. How many miles did we go during that time? We went from a mile 100 to mile marker 210. So that's 110 miles, right? How long did we drive? Well, that gap between 1 p.m. and 3 p.m., the difference, the H, is 2 hours, right? So we drove 110 miles in 2 hours. That's about 55 miles per hour is what we say our average speed is, or our average rate of change. Okay. So there's some very realistic, hands-on examples of why we would need this average rate of change thing. And that's what we're trying to play with here and see what we're up to. So um, let me hang on just a second. Let me find another example. Okay, so let's say this is straight out of your book. There's an example that says you work for a company that makes planters. Okay. And somebody in the back office, somebody is paid to figure out their revenue function. So they come up with this function: R of x equals 20x minus 0.02 x squared. And they tell you 0 is less than or equal to x is less than or equal to 1,000. And that would be units or planters that we are able to sell, right? Because this is revenue, this is money coming in, revenue. Okay. So somehow they figured out that you can talk about the money that you're going to bring in by using this thing. And what is this little bit over here? Tell me. 0 is the smallest. Well, sure, I could sell no planters, right? Okay. But 1,000 is the biggest. Okay. So what they're telling me is that my model has a limitation. It only goes up to 1,000 planters. And that's probably because, I don't know, maybe there's if I'm going to make more than 1,000, then maybe there's a bulk sale or something that I can do that might change my cost, might change my revenue, that kind of thing. So this is what they think this model is good for. Part A says, find the change in revenue when we go from 100 planters sold to 400 planters sold. Okay, so the revenue is going to go up, right? But it's not going up in a linear fashion, right? This equation, by the way, let's talk about this equation. This equation is a parabola because it's x squared is my leading exponent, right? And it's an upside down parabola because this leading coefficient is negative. Okay. So what we know is my revenue will increase, but at some point it's coming back down, right? So basically, I don't know, maybe people just don't want a ton of those. Maybe as I get more, my cost increases because I have to pay more people to work. I don't know what that is, but that's what they've decided the revenue function is. Okay. All right. So we need to do a little bit of work here because I want to use my average rate of change, right? But all I know is my input values here, right? So 100 planters is my X, and then 400 planters is my X. So I need to find 2 points before I can do anything else. Okay. What if X is 100? What if X is 400? That's what I need to know because I don't have any outputs for this, right? I only have number of planters sold. Okay. So we're going to plug in everywhere we see the X, we're going to plug in 100. Okay. I need to do minus 0.02, and I'm going to put it in parentheses, 100 squared. Oops, let me get out of the exponent. There we go. And I think that it's $1,800. Okay, so if you're not sure, when I did 100 squared times the 0.02, that was only 200, and we had 2,000 minus the 200. So punch it all out, do it how you need to. Here, let me show it. 20 times the 100 That's what I punched into my calculator. This is 2,000. Oops, 2,000 minus and hang on. I think I punched something wrong. So 0.02 times 100 squared is going to be 10,000, right? Because it's 4 zeros. Okay. Now let me do that step again because 0.02 times 10,000. Get enough zeros in there, I think. That's 200. So that was 200, we said. So this is my green pen's running out of ink. I'm sorry. 2,000 minus 200, that's 1,800. And that is exactly what we said for that guy, right? But that's how we work it out. Sorry. And then for the, let me switch ink colors. For the 400 guy, same thing. It's going to be 20 times 400 minus 0.02 times 400 squared. Okay, so let's punch that on our calculator. I'm going to do it in pieces this time so we see it all. 20 times 400, that's 8,000, right? And 400 squared, that's 16,000. I'm sorry, 160. Yes, 160,000 times the 0.02. Okay, so that's 3,200. Okay, so I can do that pretty easily. 8,000, as long as I get the right number of zeros, minus 3,200. This is 4,800. So sure enough, we've got two different points, 4,800. I've got my 2 points. I did the math here. That pencil's not working for me. Sorry. Okay. I got my 2 points. I feel good about that. Now, we haven't started the problem yet because the problem said find the change in revenue when we go between those, right? When we start at 100 and we go up to 400 planters. So, what we need to do is we need to do our average rate of change, right? Sorry. Average rate of change. Well, we know that it's the f of x plus h guy, or the y2, 4,800, minus the y1, which is the 1,800, or in the function, the difference quotient, we see that's f of x plus h minus f of x, right? Okay. Over, and on the bottom, I've got 400 minus 100. Now notice, okay, if you're really paying attention, what's the gap between these two x values? To go from 100 to 400. My gap, my h must have been 300, right? Okay, so we could have known that beforehand. And now look what I'm doing here on the bottom. 400 minus 100. Sure enough, I'm going to have 300 on the bottom, right? Okay, and this actually works out very nicely because 4,800 minus 1,800 on the top, that's 3,000, and I can get rid of 2 zeros, right? So this is 30 divided by 3. Oh, I'm sorry, that was all over h. Let me finish that. This is my difference quotient. Okay, 30 divided by 3, and we know 30 divided by 3 is a 10. Okay, so the average rate of change there is a 10. Okay. So when I look at the AROC function here, what we're saying is we let the x be 100, the gap, the h, is a 300. This was the x, f of x, put in 100, and again, the gap is a 300. So we did exactly this, right? What's the functional value when we had x plus h? 100 plus 300. Well, that was the functional value when we had 400. Okay, got it. This is just the functional value when we put in 100. That's that. Got it. And on the bottom, the difference between the 2 points, that's the gap. That's the 300. Oh, look, we got it. No problem. So we're doing the same thing we were doing whenever we dealt with slope formula. It's just a little bit more formalized. So don't let it throw you is my point there. Okay. All right. So secant line passes through 2 points. Okay. And that's all fine and dandy. But eventually, let me pull my graph back over here. Eventually, what we're going to say is I'm tired of finding the slope between these 2 points. I want to just do 1 point. So let's see what that graph would look like. That other graph's getting a little bit full, so I'm going to put it here. We're still dealing with the y equals x squared guy. Okay. But the idea here is instead of me punching in 2 points, can I just do 1 point? Okay. So that is a totally different graph. That is called a tangent. Tangent line. Okay. And what's the difference between that and a secant line? A tangent line crosses the graph of a curve in one location. Just one spot. Okay. It's no longer a secant line. It's only going to graph in one location. One location. Okay. So what's that called? That's going to be instant rate of change. Instead of me averaging between 2 different points, average rate of change, I want to know what's happening right there in that one spot. So I want instant rate of change right now. Okay, I don't want to have to average it anymore. And of course, we're going to call that IROC, of course. So instant rate of change. And the nice thing is that we've actually already been kind of playing with that formula. It is the formula for the derivative by definition. That's what we said we were going to do. And that's IROC, which is equal to, and it looks just like the AROC one, except for we're going to add one little step here. The limit as h goes to 0. Okay, there's one little step out in front. Okay, don't let it throw you. So this guy is what we're going to be dealing with. And they call it the derivative, and I'm just going to throw this in here. The notation for the derivative looks like that with a little apostrophe on it. We call it f prime. Okay, or the derivative. Okay, so when you see all of this together, when you go into your homework, if they have that little apostrophe up there, you know they want me to find the derivative. That's what they're looking for. And the derivative is what happens in the instant moment right here in this one point. And so in your head, I hope you start thinking these things. Okay, tangent has 1 point. Okay. That's instant, okay? And that's derivative. That's f prime. So all those things go together. When we go to 1 point, hey, now we're talking derivative. Okay, so that's what throws us into the calculus end of things. So we know IROC is the slope of the line that is tangent line to the curve. And of course, curve. Okay, of course, if I put my, say I put my tangent line over here and draw a tangent line there, only at 1 point. Well, what do we know about this slope of this line? That's positive, right? Because we're going uphill. And what do we know about this slope of this line? It's negative. So what you get for your instant tangent line, that that rate of change, it depends on where you put your point. Okay, so it's all going to depend on where I start my point out. Okay, so you're going to see some different definitions or directions for this stuff. It's going to say stuff like, here's my example. Use the instant rate of change, IROC, to find the slope of a tangent line for y equals x squared. We're sticking with this guy. Okay, when you don't have 2 points. Okay, if I don't have any points, that means I have to stay very, very, very generic, right? Okay, so we are going to use this formula right here, and we're going to do what's called a 4-step process. 4-step process. Okay. And this is what you're going to see as you go through your homework. They're going to say, work the 4-step process. And yes, you have to do it step by step by step, and you have to do it manually. And even if you know some shortcuts because you've had a calculus class before, we'll get to shortcuts, but you cannot do your shortcuts here. You have to do all of this by hand. Definition first, then we'll get shortcuts later. Okay. So 4-step process. What does that look like? It's going to be step 1 here, step 2 here, step 3 here, and last but not least is step 4 there. Okay, so we will work through it. We'll do a couple of these so you see them. You'll have a chance to work on it. But those are the 4 steps. First, find this, then subtract that, then divide that. Then last but not least, we're going to take that take that limit. We'll talk about the limit idea in a minute. Don't stress out about that. And I'm going to walk you through one of these. Okay, so I'm going to stick with this y equals x squared guy because he's a nice one for me to start with. We'll do some more complicated stuff later. Y equals x squared. Okay, so step 1. We need to find f of x plus h. Okay, and I noticed that sometimes in your book and in your My Math Lab homework, they'll say a plus h. It's okay, just substitute an a everywhere you see an x. It's not a big deal. Okay, so what did we say earlier? We're going everywhere we see an x instead of an x. Remember, this is my f of x. Y equals f of x. Those are the same. This is my functional value. So I'm going to plug in x plus h everywhere I see x. So that looks like x plus h squared. Hey, we did this one a little while ago. X plus h times x plus h. And if you don't remember, work it out. I remember, so I'm going to skip a little bit ahead. Anytime I have x plus h squared, I get x squared plus 2xh plus h squared. Okay, so that's my step 1. All right. Step 2. Oh, my green pen. I'm sad to lose my green pen. I'll have to find another one. Okay, step 2. Okay, find f of x plus h minus f of x. Okay, so the only thing we're going to do is we're going to take the guy that we had before and we're going to subtract the original f of x function. Okay, so x squared plus 2xh plus h squared minus, because there's a minus in the formula, whatever that original function is. Now I'm going to put parentheses here. Okay, I'm putting parentheses not because I necessarily need them because this is only one term, but because when we get a more complicated function than just x squared, we're going to need to what? Distribute that negative sign through. That's right. So if there were 2 or 3 terms back here, we would need to distribute this negative sign. And we're going to have to make sure we do that. Okay. In this one, it's only one term, x squared. So it's not too bad. I can very quickly say, oh, look, I can simplify that. Those will go away. And what we get here is 2xh plus h squared. Okay. So you're not done until you've cleaned it up a little bit and simplified it. Okay. So let's come back here. We did step 1. We've subtracted this guy. That's step 2. Step 3 is divide all that by h. That's step 3. Okay. So we've got, let me find f of x plus h minus f of x all over h. So it's add that extra step, right? So sure enough, we've got 2xh plus h squared. We're dividing by an h. Remember earlier I said that if we've done it right, hopefully the only stuff that's left over is stuff that has h's in it. So that's good. I like this. All of them have h's, but I look at it and I say, hey, I need to get rid of that h if I can. The solution there is factor, pull out an h, and then sure enough, there's an h on the top, there's an h on the bottom. Anything divided by itself is 1. Those will go away. H over h is 1. And what I get is 2x plus h. Okay. So that's step 3. So all of that is just exactly like the AROC that we saw before. Okay. And we're just going to add in this one extra step, which is this limit step. So I'm going to talk about it for just a second. But find the limit as h goes to 0. I'm not going to write all this every time. I'm just putting it out here so you see what the 4 steps are, because there are 4 steps. It gets a little bit complicated. So what we're trying to do is find the limit as h goes to 0 of 2x plus h, because that's what all of this stuff is, right? We found that, so we can put it right there. Okay. So take a pause. What the heck does that mean? Okay, this is a very, very calculus concept. And if you were in my Math 1325 class, before we got to this point in the semester, we would have spent about 2 to 3 weeks working on various kinds of limits and how things happen, what's going on. Okay, so normally in a classroom, I give a very concrete example, but because I'm on a video, let me do this with my hands. Okay. So say that I'm standing here where the left hand is, and there's a wall over here where my right hand is. Okay. And I want to go half the distance till I get to the wall. Okay. Then I want to go half the distance again till I get to the wall. Then half the distance again till I get to the wall. Then half the distance again. And sooner or later, we're going to say, oh, basically, I'm bumping up against the wall, right? Okay. I'm limited by the fact that I have a wall there. As I get closer and closer and closer, I know there's actually still a space there, right, between my hands, but it looks like I'm just bumping up against each other. So eventually we're going to say, what the heck? Just let it be that the distance between my hands is 0. Okay. So remember here that what we're doing in this particular case is that h is the gap between these 2 points. Let me go back to my here. Okay, we had a gap, we took half, we took half, we took half. Okay, so that's the same idea. And then in the most recent one, when we're doing instant rate of change, we say, oh, no gap at all. The h equals 0. Okay, because there's not 2 points anymore, they're just 1 point. Or you could think, hey, there were 2 points, but now they're on top of each other. Okay, there's no gap at all between them. The h is 0. Okay, so the idea here is, okay, it's a very intense calculus concept that I am literally explaining in 2 minutes. The idea here is basically, let's just act like there's no gap at all, okay? So it's called taking the limit as h goes to 0. Take the limit as h goes to 0, and in our cap is the gap disappears, basically, is what we're saying in our case. Okay. There's other ways to take a limit. And if you've taken a 1325 class, what we've heard from the College of Business is that the limits kind of stress the students out. It's a very mathy, it's a very theoretical kind of concept. So we are not going to go in depth into limits. This is what you're going to do. Okay. We're going to take the limit as h goes to 0. What that means is we're going to take everywhere we see an h and we're going to plug in 0. Okay. Now, this little notation, the limit as h goes to 0, that's like any other notation you've got. So just as a point over here, scratch paper. If I took the square root of 4, you would say, well, I'd say, what's the square root of 4? And you say, square root of 4 is 2, Dr. Webster. And I'd say, you're right. Okay. When you're finished, what happened to the square root? It just went away, right? We took it. It's gone. Okay. Same thing if we did something like 12 divided by 3. We're taking the division here, right? We're dividing these. 12 divided by 3, you would just say 4. What happens to this division symbol? It just goes away, right? Because we did that. We did the math. Okay. So the idea here is I'm going to take the limit as h goes to 0. And once I take that, I do that math, this goes away. Okay. So that's going to go away just like the square root goes away, just like the division bar goes away. This h, we're going to plug in a 0 there. So everywhere I see an h, I'm putting in a 0. And basically that term's just going to go away. Okay. So what does it mean when I say take the limit as h goes to 0 of 2x plus h? Let me rewrite this because I wrote all over that. Limit as h goes to 0, 2x plus h. What would normally take a 2 to 3 week lesson in 1325, you are literally going to go, hey, I'm going to plug in 0 for h. I'm going to assume the gap between those two things is gone. Okay. And when I do that, the limit part goes away. 2x plus 0 is just 2x, right? And we're done. Okay. So it's going to depend, the instant rate of change is going to depend on what my x value is. Okay. So when we started this, we said we're going to do this very generically. Here's where I started it. Okay. Use IROC to find the slope of a tangent line. Okay. For this guy, when you don't have 2 points. So we did our 4-step process. Step 1, f of x plus h. Step 2, subtract the original function. Step 3, divide by h. Step 4 is take the limit as h goes to 0, and you end up with this. And the notation looks like the instant rate of change for this function is f prime of x or just 2x. Okay. Again, f prime of x. That notation with the little apostrophe on it, that's how we know we took the derivative. Okay. And then what happens? Well, it depends on what point you give me. Okay. The instant rate of change. If you say at x equals 1, oh, no problem. Plug in x equals 1. 2 times 1, that's a 2. Okay. Then my derivative at x equals 1 would be 2. Does that make sense? So that's going to look something like this. F prime of 1, plug in a 1, because that's what happens when you substitute, you get a 2. What if I wanted to know the derivative at 3? Okay, here's my 2x, that's my derivative. Put in a 3, that's a 6. right? Here's a fun one for you. Think about it. F prime of 0. What do you get? Plug in a 0, Dr. Webster. We get 2. Oh, I am just a mess. 2 times 0 is 0. Yeah, see, that's what I get for making funny noises, funny sounds. I got distracted for just a half a second. Okay, so that's the idea that's going on behind the scenes whenever we're dealing with one of these instant rate of change guys. Okay. Um, let me just have a slight second to talk about when we will have an issue with this, because I've got that in my notes. So I want to make sure that I point this out. So the function that we're dealing with here, f of x was x squared, right? Okay. We've got this limit as h goes to 0. When would I have an issue with plugging in an issue? When would I have an issue with plugging in h equals 0? Okay. Not in something like this, f equals x squared, f of x equals x squared, I'm good. But what if it was something like f of x equals 1 over x? Okay. And I want to end up dividing by h equals 0, right? I'm going to have to worry about, that's not quite right either. I'm sorry. I'm trying to come up with an example, and I had it in my notes that we have to watch out for it, but I don't have an example. Okay, so let me just put it like this. Okay, you can't divide by 0. So h by itself in the denominator. Let me just put it like that. That's not a good example. I'm sorry. Okay, so h by itself in the denominator, that's we're going to have a domain issue. So we're going to watch out for those whenever we get going on this. Okay. But for right now, we should be okay. I would like for everybody to practice this. We're going to practice a fairly simple one, and then I'm going to do a little bit more intricate one. So if everybody will use this example, f of x equals 5x minus 12. Okay. And I want you to use the instant rate of change. Okay. 4-step process and work them all out to find f prime of x. Okay. By the definition. No shortcuts yet. I know if you know some shortcuts, that's great. Hold on to that idea, but I'm going to push pause. I'm going to work this one out for myself. You should push pause as well. And when you're done, come back and let's see if you got what I got. Okay, so hopefully you work through them. Again, you don't have to write exactly all of this stuff, but at first I like to write it to help people out. So the first step is f of x plus h. I plugged in x plus h and I got this 5x plus 5h minus 12. Second step is subtract the original function. So I did that. And again, notice that I put parentheses and notice that I distribute this negative sign through. You have to do that, especially if you're really prone to losing a negative sign like many of us are. I do it too. You have to do that because what happens is the minus 5x and the negative in the negative makes a positive 12. That's what causes these things to drop out, right? If I don't distribute a negative and I have a minus 12 and a minus 12, then I've got negative 24 and that guy's not going to drop out and that's going to be a problem, okay? So these need to go away. These need to go away. All those terms are gone now and I'm left with 5h. Step 3, divide by h. I just get a 5. And actually, because there are no h's left now, this is an unusual one. It's because I started with a linear equation. Because there's no h's left, I could stop there, but technically there's the step 4, which is take the limit as h goes to 0. I need to Oh, excuse me. I need to put a 0 anywhere I see an H, but I don't see an H, right? So that just basically goes away and we just have a 5. So the derivative of this original function, which was 5x minus 12, f prime of x, was just a 5. Okay, we got our answer. Okay, so let's try another one. We're going to make it a little more complicated. So you have to really pay attention as you work through all your steps. Again, I would say pause the video so that you can work through it on your own and make sure that you know how to do it. Find the instant rate of change, and this is by the 4-step process. Make sure you do longhand. On the homework in my math lab, it actually asks you, like, what's the first step? What's the second step on some of these problems? So you really need to be able to do this. But maybe pause and then come back and you can see what's going on. And I'll pause as well so that I can work through this without taking time. All right, so here's my work. I'm not going to go through it all. Pause the video and look and make sure you've got it right. Again, make sure you've distributed your negative sign through the entire thing here on step 2. Same thing for step 1, actually, because there was a minus in the function, right? So it was minus x plus h squared. So minus has to be distributed all the way through. So be really careful with your negative signs. At the end of step 2, I have 4h plus 2xh minus h squared. At the end of step 3, I have 4 plus 2x minus h. Make sure you can factor that h out of the top. And then here, we're not as lucky as in the last problem. Here we actually do have h's left over. So we have to take the limit as h goes to 0, make that guy 0. I get 4 plus 2x, and this is my f prime of x, okay, or my derivative, or my instant rate of change. All of that goes together. So if you need to go through that a little bit more in depth, pause the video, rewind, whatever you need to do so you can see all of that. Okay, so that's the idea of what's going on behind that. I have a couple of special cases that I would like to show you. What about if this happens? What about if that happens? Let me give you one more example. I'm not going to work it out. Fx equals 8x minus 2x squared. I want you to work that out, and I'm going to tell you right now, I think the derivative should be 8 minus 4x. So you work that out, do all the steps, make sure you get there all on your own, pause the video so you can do it. And make sure you really have a good grasp on this 4-step process before I make this next video, which is going to be, okay, what about some of the weird things that happen whenever we're dealing with this instant rate of change formula? So I want to do that separately. So go ahead and see what you got. Thanks.